This is a series on Project Euler problems and how to solve them. We're going to start at number 1. So the first Project Euler problem says, if we list all the natural numbers below 1,000 that are multiples of 3 or 5, we get these 4 numbers, and the sum of these is 23, because 3 plus 5 is 8, 8 plus 6 is 14, 14 plus 9 is 23. So now we would want to find the sum of all the multiples of 3 or 5 below 1,000. And the language that I'm going to be using is Python, as you can see by the file name here. So the easy way to do this is to loop over all of those numbers and keep track of the total. So what we're going to do then is to have a total variable set to 0, and then we'll loop over all of the numbers between 3 and 1,000. And you may think, okay, well, why aren't you starting at 0 because it says below 1,000? Well, if we start at 0, well, that's not going to do anything. And if we include 1 or 2, well, 1 and 2 are not multiples of 3 or 5. So we might as well just start at 3, although the answer will not make a difference. So what we can also do is see, oh, well, it says below 1,000, and therefore we shouldn't include 1,000 in our sum. So what we're going to do then is do a for loop on all the numbers below 1,000. And so the variable I'm going to choose here is n, that's the name of my variable, and the function range allows us to go over certain values. So if we want to go up to 1,000, then we would just say for n in range 1,000. But if I want to start at a particular number, say 3, then I write this as 3, 1,000. Starting number is 3, ending number is 1,000, and range does not include the value in the second value right here. So it goes up to 999, which is exactly what we want. So then all we need to check is, well, is n divisible by 3 or 5? So then all we need to do is say if n modulo 3, which means take the remainder when you divide by 3. So if there's no remainder, meaning that it's a multiple, then that means it's a multiple of 3, or n is a multiple of 5, which case we would do very similar thing except with 5. So if either of those is true, then we got to add that value onto our total. So we say total plus equals n, where this means we're just adding on the value of n onto total. And then all we need to do at the end is print the total. So in this series, I'm not going to actually run the code. I'm just going to show you my process in trying to solve the problem. So if you want to actually submit this, you would have to code this up and understand it yourself. So this works, and it'll give you whatever the right answer is. But there's actually a much faster way. So notice here that the values that we're going over are from 3 to 1,000. So if I put, say, 10 trillion into here, then this loop will iterate 10 trillion times, and that'll be extremely slow. So there's actually something that we should notice here. So what are we really doing? We're really adding the multiples of 3 and the multiples of 5. So let's list out the multiples of 3 in a summation like this. So here are all the multiples of 3 in this case that we are considering, and let's look at the ones that are a multiple of 5 also. So these are all the multiples of 5. Well, if you just simply add all the numbers in here with all the numbers in here, you're actually going to get some duplicates. So if I continue the 3 series for one more step, you notice that we're adding 15 twice. So what we need to do then is to subtract all the multiples of 15, because for all the multiples of 15, we're going to see them twice, once up here in the 3 sum and once in the 5 sum. So we need to subtract 15 plus 30 plus 45 plus dot, 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 etc. So what we need to do then is to say, okay, well, the value of n that I need to give in here is based on how far this sum needs to go. So what is another way we can look at this sum? Well, we can look at this and see, oh, Well, all of these are a multiple of 3, so let's just take a 3 out of the sum. So 3 times, well, if you take out what's left, you have 1 plus 2 plus 3 plus dot 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 plus 3, 3, 3 in this case. And if we do the same thing for the 5 sum, we have 5 times 1 plus 2 plus 3 plus dot 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 plus, let's see, what is it in this case? 199. And what do we notice about these? So 333 looks suspiciously similar to 1,000 divided by 3. And similarly for the 5 sum, and indeed that's the case. So what you need to do then is to write a sum that goes over these values. Well, if it starts at 1 and it goes up by 1 every single time, there's actually a shorthand for this. So 1 plus 2 plus 3 plus dot 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 plus n is always equal to n times n plus 1 divided by 2. So another way to rewrite this sum for a 3 is 3 times, well, n in this case is 333, so times 333 times 334 divided by 2. And then similarly for the 5 sum, it would be 5 times 199 times 200 divided by 2. And whatever that value is, that's the 5 sum. And then you can do something similar for the 15 sum. So all you really need to do then is to write a program that figures out what these values are. So in this case, it's 1,000 divided by 3 and then rounded down. And then here, it's very similar. It's 1,000 divided by 5, and then you go to one value less. And then I'll let you think about how would you do something similar for the 15 sum. So the key to understand here is that there's actually a very repetitive pattern here, which is that the values for 3 that we're looking at have a very similar pattern. This is what is called an arithmetic progression. So the progression means that each term is 3 larger or a fixed value larger than the one before it. And similarly for the 5 sum and similar for the 15 sum. And because it's an arithmetic progression, we can actually figure out what the sum actually is because it's an arithmetic progression. So I hope that was interesting. I hope you like this series, and I'll see you next time.